Okay, I think the numbers have stabilized. So welcome everyone to the webinar series of the UK Climate Resilience Programme. We have a talk by Professor Julien Harou today. He's going to talk to us about seeking water resource resilience at multiple scales in England and Wales. And we also have Steve Moncaster, who will provide a response from an industry perspective. Steve is Technical Director at Water Resources East. I'm going to tell you just a couple of news that have come about briefly, and then I'll hand over to Julien to take us through the research that he's been doing, both in the program and I think beyond as well. So I think most of you who've come to our webinar series before will know how to engage. So we'll do the presentations first, and then we'll do the Q&A and discussion. Feel free to start posting questions in the Q&A at any point in time. There's this thumbs up that you can use to upvote your favorite questions. And yeah, most attendees will remain muted unless we enable that function. We record the webinars, so we'll put this in the website afterwards, and you'll hear about that as well. If you do have any technical problems, use the chat function, please. And yeah, feel free to use the Twitter handle and the hashtag, and do go to our website for more information. So just a couple of news before we start off. We had a couple of days actually where climate adaptation was at a very high level, being discussed at a very high level policy-wise. So I just wanted to mention, so that if people are interested, go and have a look at the Climate Adaptation Summit that happened over the last couple of days. You know, many global leaders attended, making a lot of commitments to accelerate adaptation and build resilience. So the UK launched a new, with other partners, an adaptation action coalition. And then there was also the launch, not only, you know, a lot of you might have heard of the race to net zero, but the UN high-level champions also started a race to resilience, to bring on board businesses, NGOs, government, cities, to the race to resilience. So do check that out, because there really is a lot of activity going on. There was there was a forum on cities, there was a focus on water infrastructure, and many different areas. So well worth having a look, and very relevant to the program. The only other announcement I wanted to make was around a hackathon that the Met Office is running. So it's a 2-day virtual event in the middle of March. And it really tries to build resilience to climate change by exploring different ways of visualizing the UK climate projections 2018, and possibly combining them with other types of data as well. So it's very relevant to the program. It has a focus on 3 main areas: marine and coastal, nature-based solutions, and sustainable development, both at home and abroad. And some of this could be then showcased at COP26. So if you're interested, email the Met Office at that email address, and this will all go on the website as well. So without further ado, I will hand over to Julien, who is a chair in water management at the University of Manchester. Julien, would you like to share your screen? Okay, over to you. We can see the slides.
Okay. Can you hear me as well?
Yeah, we can hear you and we can see the slides. Yeah, over to you.
Great. All right. Well, thanks. Thanks, Suraje. Thanks to the organizers, and thanks for Steve for agreeing to be a respondent here. I'm going to go through a series of like Suraje hinted at. I sort of expanded because on the scope of what I was going to talk about today, because this UK climate resilience impacts several pieces of work that we've been involved in with various stakeholders over the past years. So I just wanted to give a summary of some of the work at national, regional, and landscape scales. And so it's, you know, in summary, this will look more like a summary of 3 talks. Okay. Right. So the first is work that we've been doing with RAPID and with Natural Resource Wales, looking at national scale water supply demand planning. And that's really thinking, is there trying to identify the strategic benefits of thinking of a water supply system at national scale, and what are the cost and resilience implications of that. So let me review that as a first topic. So the aim of this project that we did with RAPID was to identify efficient mixes of future new supplies and transfers options nationally using existing water company data that the companies provide in the water resource management plan process. And this national supply demand model provides an unconstrained top-down look at how these different independent water resource zones could work together at national scale to cost effectively meet demands, potentially using some transfers that are not currently in company plans. So this is what I'm going to review first. For this, we expanded a tool that we had initially built with the Environment Agency as part of the national framework for water resources. But before I talk about the tool, let's just quickly look at the overall situation. Although this model can run for any number of years, for this analysis, we just looked at an overview for 2050. And this slide is just showing the supply demand balance that are, the supply demand balances that are available, that are currently planned for 2050. On the left panel is considering 1 in 200 year drought resilience, and the right panel is the 1 in 500 year. And you can see that there's some blue areas in the north, but generally there's quite a bit of neutral, just barely making it gray areas, and then some light grayish red or red areas where there's a predicted supply demand deficit by 2050. So, this is just to say that it's justified to look at this. There's areas, large areas in the UK, in the England and Wales, where we think that in the next 20 years, 30 years, we're not going to be able to meet demand. So that's sort of the motivation and the scope. The other thing going on is that the regulators and water company managers have realized that there aren't, the number of options that have been identified for water supply are unevenly distributed throughout the country, and the cost implications are also unevenly. So if you look, this is just a quick overview slide. If you look at the top left, you can see that for small, just providing 10 million liters per day, there's a lot of regions that can provide that water for cheap. But if you look at the bottom right, if you're looking at supplying water at 10 times the amount, you can see that there's much more grayed out zones, that water supply zones that can't supply that demand. And so there's only a few that have available supply options to meet 100 million liters per day. And this one looks even further. The bottom right plot is looking at, is there any, what are with the current water supply options that the companies have proposed? You can see at the bottom right that there's only the London zone, which has proposed enough potential new supplies to meet, that amount to 500 million liters per day. So this is just to summarize that, the demand and supply of water resources in their cost is a complex spatial problem, and there definitely is a deficit by 2050 that needs to be addressed in some way. And so the natural question for planners in the UK is, are we looking at this? Are we being as collaborative as we can, and is that going to allow cost-effective solutions? I'll skip that one. And the suspicion was that if you look here, the red lines are the water transfers that water companies are currently proposing. And you can see that they're relatively few compared to the orange ones, which are all the ones that they tested. And then all the green ones are all the potential feasible water transfers. So you can see that there's a lot of, if you look at the red lines compared to the green lines, there's a lot more possible water transfers that could be considered than the ones that have been considered in detail and costed up by water companies in red. And so that's really what this modeling tool is trying to do. It can work in simulation mode and in optimization mode. And in simulation mode, it's just looking at the annual supply-demand balance of any subregion of these water resource zones. And in search mode, or multi-objective optimization mode, it's trying to see, are there cost-effective ways to minimize the cost and meet the demand across with different spatial solutions. So let's have a look. So right away, this is the kind of result that's produced by this model. You can see that it can be run for different scenarios. The orange, let's just focus. So there's, right here we have 3 demand scenarios: high demands, 2019 planned demands, and lower demands, or demands that would respond to increased efficiency. And those are in blue, orange, and green. So just look at the orange one, because we don't have a lot of time. What this is showing you is, on the y-axis you have the cost of local supplies, and on the x-axis you have cost of transfers. And what this is showing is that for, depending on how intensively you want to transfer water between regions, there's just a whole wide range of ways that you can invest in infrastructure to meet the future supply-demand balance by 2050. And each one of these points is a cost-effective, or the most cost-effective way to meet any combination of how much money you spend on supplies locally and how much you spent on water transfers. So the idea here is really to let water planners and regulators think about, how much, to obtain these resilience targets we have of meeting the 200 or 500 year predicted droughts. What kind of solution, what kind of national scale water supply solution do we want? To what extent do we want to depend on transferring water? And you can see in this orange line, there's one point that's been singled out as the least cost portfolio. Now, the ones next to it are almost as cheap, so there's no reason to focus exclusively on that. But I just wanted to underline that each one of these points is referring to a full national cost optimization for a certain demand and resilience level. So there's a lot of information in that previous plot, because each one of those points was leading to what we see here graphically. And you can see, so this is not trivial to interpret. On the right-hand side, you have the scale of the water supply, so how much is developed locally. Those are the supply options in different shades of purple. And then the different shades of green and blue on the left is telling you for each of these water transfers, how much is involved, how much water is involved. And so you can see that, so it's not the length of the lines that you should be looking at, because those are just going from centroid to centroid of these water resource zones, but it's the color of these little transfers that shows the extent of the transfers. But you can see a nice spatial pattern there, where there's a lot of short distance and small transfers going on all over the east and south of England, and then some larger transfers from the center of the country. So certainly a lot to think about there. Obviously, we're only seeing these superficially here, but this has led to lots of interesting conversations with planners and regulators. The last thing I wanted to show, obviously, you don't look at the detail of the efficiency plot here, but here we considered, if you allowed the companies to transfer only within their company boundaries, or if you allowed them to transfer within regions but not outside of their region, or if you allowed the transfers to occur countrywide, how would that impact the ability to meet the supply-demand deficit, and how would that impact the costs? And it turns out that it was quite strong. There's only when you allow transfers within the regions that you can actually meet those 2050 deficits, and so or having national scale transfers. So that was interesting to learn that the problem is infeasible unless you allow quite a bit of cooperation between regions. And of course, so for each one of these spatially constrained scenarios of how much you use transfers, we can then generate these different plots which show for each one of those extensive transfers what would be the best way, within the constraint of that transfer scenario, what would be the best way to organize. So you can see there's obviously a lot of information here. I think the main take-home point here is that the old least cost planning that we used to do has evolved quite a bit, and there's the ability to think about much more, more policy options and embed more complexity in the water design problem. So, here are some initial lessons from these results, but I won't focus on these now because time is passing quickly. And I'll refer you to the report on this that'll come out in a few months from Rapid and Ofwat. Okay, the next work is work that we've done directly with Steve Moncaster and with Water Resource East. This is looking at no longer at the national scale, but at regional scale. And this is, unlike the previous one, which was a very water supply focused study, this is looking at aiming for resilience in a multi-sector sense at the regional scale. So Water Resource East, Steve will probably say a few words about it. It's a really exciting multi-sector project of long-term management and planning of water in East Anglia and how water can interact with other economic and social sectors of water use. You can see the scope here, the geographical scope, and obviously there's increasing demand and climate change. There's various challenges, and you can see this covers really the whole east of England. So the technical question we had is what combination of supply, demand, and management and policy interventions and the groupings thereof, which would meet stakeholder performance requirements efficiently under future uncertainty. So that was our question. The sectors we considered were public water supply, agriculture, environment, and energy. And for each of those, we had specific objectives and performance metrics that I won't go into detail here, but suffice to say that we consulted over a multi-year process with each of these sectors to understand really what were their constraints and motivations and aspirations so that we could try to do a similar multi-objective optimization, but looking at these different multi-sector needs. I think I'll skip this one. This is just giving sort of the conceptual technical approach. So we followed what could be called loosely a robust decision-making approach, where we assess uncertainties, we assess the actions or levers, I'm looking at the top box here. We use a simulation model to encapsulate all the relationships between the different elements of the system, and then we track metrics of performance. And where we go perhaps beyond robust decision-making is that we connect that conceptual framework to multi-objective optimization, or others would call it multi-criteria search, or just a way to search through lots of options efficiently. And so that's what we're doing in this project. So we create a simulator, we track metrics that we care about, and we do that as hinted at in this slide at different scales and for different stakeholder groups. So that was a multi-year process to pick the scales and the metrics involved in that for each of the sectors. And a quick summary here, I'm not going to go through them in detail, but you can see that there was quite a variety of different interests for each of these sectors. And I won't go through them in detail because this is an overview talk. The geography of the system, it looks like this. Once again, we build a simulation model initially, just like we did at national scale. Here you can see there's a lot more detail, and we include, so there's, the rivers and all the infrastructure, and we use this Pi-to-Bjor model, which is the same model that we used at the national scale. So that's a very flexible model, which is open source, which you can read about in the reference there. And the interventions, there's a whole wealth of spatial interventions that we're looking at. You can see here, they range from reservoirs to groundwater to ASR, conjunctive use of groundwater and surface water, desalination, effluent reuse. Lots of options there in purple, and including transfers. And if you're tracking all the benefits to the different sectors, there's basically billions and billions and billions of different ways you can invest in the water, energy, food, environment of East Anglia and of East England. And the purpose of this methodology was just to try to make the computer help through the search of all those options to try to identify robust and multi-criteria acceptable solutions. And so if you're interested in modeling and optimization, this is a robust many-objective evolutionary optimization. So we connect that regional simulator to an algorithm, and we track which interventions do well. And what that looks like in Okay, so here for people interested in the formality, so the objectives are here, some are minimized, some are maximized. These are basically, we're either minimizing or maximizing some of those metrics that the stakeholders selected. The decisions are which investments to make, which interventions, and then the policies. There's different water management policies regarding agricultural water use or environmental flow, and those are translated into decisions that the optimization model is trying to assess. Now, we don't have time to look at results today, but the results look something like this. You have your performance metrics are vertical axes, and then each one of these lines is an investment package for East England that meets that specific combination of preferences. So if you want to do really well on total cost, well, you're going to pick the very top of that axis on the left. And depending on where each line falls across each of these axes, that'll be an investment plan for the region that follows different priorities. So this is a neutral, this is showing all the possibilities in a single plot. And so we spent months and years looking at, because here this looks confusing, but there's only about 200 solutions or 150 that are outlined here, but the algorithm must have analyzed, in the millions of billions. So this is actually a really reduced set, and the stakeholders were really pleased to be able to filter through these very carefully and try to learn what they were implying. I'll quickly, and so then, once you pick one of these lines, then you can start to map out spatially, what are the implications. So one of those lines that stakeholders liked, when we looked at, okay, what did that imply for leakage, for agricultural supply, for groundwater abstraction, we could make maps showing them specifically what was being implemented in any of those one lines. So that's what this is showing. The other thing that we're doing is we're now putting this system on a nice web-based interface so that the stakeholders can really interact with this and make it less of a black box. They can really get their hands dirty looking at the details. So for this regional scale, quick discussion would be that this sophisticated performance-based multi-sector planning is both possible and practical. We've done it. It took us several years with Steve, but we did it, and we're now doing a third phase of this, or a third try, if you will. The one thing I wasn't able to show you is that we track both global performance for the whole region, but also local performance. And so one of the things we learned here is that good regional performance doesn't always imply good or even acceptable local performance. So there's a lot of trade-offs to be made between overall good for the region and sufficiently good for any local catchment or sub-region. So that was very interesting. Generally, this approach helps identify portfolios of interventions that meet and balance stakeholder aspirations, and future work will address further water, energy, and water supply food synergies, and maybe look at adaptive planning. Okay, I'm going to try to stick towards 20 minutes, but I'm rapidly moving towards that. So the last scale that we'd like to look at resilience and using similar methods is really at the catchment scale, or what we could call the local scale. And this is the work that was specifically funded by this NERC grant. And this was done in collaboration with the Jülich Research Center in Germany and with colleagues at Southampton. And let me just show you a quick overview of what that's like. So we're using the same overall method, which is you link a physically based simulator to a search algorithm. But the question here is, if we looked at the local scale, could we look at land use decisions? So can you make water management and water infrastructure decisions synergistically with land use decisions? And so the question here is, what land cover classes, if you consider forest, cropland, grassland, and bare soil, well, what combination of these promote a series of objectives that you might have, like food production, energy production? And so for energy here, we look at hydropower, or, because this is a little synthetic example that I'll show you first, we look at either leaving bare land to put in solar power, or, solar PV, or using hydropower, and then flood control benefits. We also look to track and optimize land use diversity, because you don't want you don't want land all occupied by the same land use. So for, just to show kind of the theoretical framework here, we're going to do a really simple system, which is just a strip with 10 land use plots. And that flows into a city, which is that house that you see. And then that city, so obviously there's a flood issue there. You don't want too much water flowing into the city. On those land use cells, you can see that you have solar or agriculture. And then finally, you have a hydropower. You can see that the water after the city, it flows into a reservoir where you have hydropower. So this is solar benefits, hydropower benefits, food production benefits, and flood control benefits in this little very synthetic system. And what we're doing here is we're using a distributed hydrological model called PowerFlow. And for the third time at the third scale, we're once again using this open source water management simulator called PyWR, which you can read about in that reference I provided. And we're again linking it to a search algorithm. And so similar type of results. Now each one of these lines are no longer a portfolio of infrastructure investments. They're a series of land use decisions. And so hopefully I can drive that home by showing you, okay, so let's look at each of these axes, right? So for example, on the leftmost axis is hydropower production. And because we're just looking at high level results here, just don't worry about the units. But that's the 30 is some description of how much hydropower is produced by that dam. You can see that it can go all the way down to 8. You have similar metrics that map out the performance for flood attenuation and the number of cells that have solar power, and then the number of cells that have crops. And so a perfect system, which with perfect hydropower, great flood attenuation, and lots of bare soil for solar power, and then crops everywhere, that would be a straight line across the top. But that's not possible because there are trade-offs in our decisions. So those have been optimized, and that's what this plot is mapping out. If you want to look in more detail, you can see, so take any one of these axes, see the hydropower axis, for example, on the left, and you can see all these lines that are touching it. Those are all land use portfolios that achieve that level of performance. So if you just look at the hydropower one, you can see that they start out green and then they all go all the way to red, very at the bottom, and there's about 100 of them. Well, if you look at the land use, so this is a little bit, let's just look at the top heat map here. So what this is that best land use. So remember, we simplify this as a strip of 10 land use cells. So if you wanted to make that perfect hydropower performance, the one that achieves 30, well, then you're looking at the leftmost strip. It's all blue, it's all grassland. And so that's the one that the model evaluated, produced the best hydropower. And as you go down and look at land use combinations that produce less and less hydropower, you go all the way to the right. And let me see if I can add a pointer here. You go all the way, yeah, you can see it's quite small. So this on the right here, this little strip of yellow cells is the one that you would do, if you cared about hydropower the least. And this blue one here is what you would care about if you cared about hydropower the most. So in summary, what this is showing is that you can, with this framework, you can start optimizing both water infrastructure and water management decisions with land use decisions. And I won't go into these, these are looking at the trade-offs between hydropower and flood control and different trade-offs. We're running out of time, so I just won't look at that. I'll just say that the thing that Steve's interested in, he's, I'm sure, not interested in that synthetic system with 10 cells, but we'd like to apply this framework to the Upper and Bedford Ouse catchment in East England. And so that's what you can see here. So you can see that here we're overlaying a water resource management model. Those are the black lines, sort of like a network water resource supply demand model with the land use map. And this was done by Daniela Anguilleri from Southampton. And so the question here is, we're going to start being able to ask our questions. Well, are there climate, well, not only how are synergistic land use and water management decisions, but are they impacted by climate and climate changes? And so that joins directly to this NERC work. So in my last couple of seconds here, the overall conclusions from these is that seeking resilient and multi-sector, multi-benefit water resource solutions can be tackled at different scales. We've shown 3 examples at national, regional, and catchment scale. The general approach we used over these three, which was simulation-based multi-criteria analysis and design, can be applied at these multiple scales. And this, in the last talk, we saw that the water planning approach that we used at national and regional scale it shows promise to integrate water and land planning at local scale. And so that's it. Thanks very much.
Great, thank you very much, Julien. You covered quite a lot there. I'd like to give the opportunity for Steve Moncaster to provide his response before we go to Q&A. Steve, over to you.
Thanks, Suraje. So, and thanks for having me along today. So I've got 10 minutes really just to follow up on what Julien's been talking about. And what I thought I would do was to give you some insight into the way a sort of practitioner views this stuff. And I've been working with Julien for about 10 years on robust decision making and multi-criteria search. And I think it'd be kind of helpful to understand where we use those techniques within water resource planning in the UK and why we're interested in that stuff. So a little bit about myself first. So I'm Steve Moncaster, Technical Director for Water Resources East. WRE is a multi-sector water resource planning organisation in the east of England. I work for a multi-sector board. So I have water companies represented on my board, agriculture, the environment, local authorities, and power companies. So there's about 12 guys on the boards and ladies too that represent those sectors. We also have an advisory group of 140 members of the company, also drawn from those sectors. So everything we do at the WRE is not just about water companies, it's about the way that all kind of sectors are interested in the abstraction and use of water, plan for what they need in the future. The thing we're working on at the moment is the National Framework for Water Resources, which has been published by the agency. So if you Google National Framework for Water Resources Environment Agency, you'll get to a load of DEFRA documents about the process we're in at the moment. The WRE is working with 4 other regional groups, so Water Resources West, Water Resources North, Water Resources in the Southeast and the West Country. And what we've been asked to do is to work over the next sort of 18 months to 2 years to produce a set of regional plans that when you add them up together, give a kind of a coherent strategy for water resource development and use in England over the next 25 years. And sort of generally what we're planning for is climate change, growth, environmental need, and a lot of stuff that traditionally water companies have done. In WRE, because we are multi-sector, we also take more of an interest in what's going on in the energy and manufacturing sectors, and there's a massive link, we think, there to net zero carbon and the transition to the hydrogen economy. And we also tend to think a bit harder about what's going on in agriculture as well. And of course, those guys in ag are going to be affected by Brexit and changes to the CAP regime and the requirement to drive productivity increases in a post-Brexit world as well. So when we look at our planning problem regionally, nationally, what we see over the 25 years is a lot of competition for a set of resources which are going to become increasingly scarce. And I suppose the key issues are managing uncertainty and the risks that go with it, because over a 25-year period, lots of things that we're planning for are very uncertain, but at the same time, the infrastructure that we need to deal with some of that stuff is really big and very expensive. So you don't have to go too far before you get into quite difficult set of conversations about what you actually want the money for and what people are getting in return. So uncertainty, risk, and cost is kind of an issue for us to deal with. And then the other one, particularly for us, but also for everybody else actually as well, is keeping everybody happy. So how across a multi-sector regional planning effort do you get the right balance of interests in terms of the plans and the strategies that you take forward. Now, the reason we've ended up working with Julien, and it has been great over the last 10 years, is that historically, water resource planning in England was a bit of a minority sport. So it was for the water companies and the regulators, single sector, usually single company, usually focused on a single deterministic forecast of the balance between supply and demand. And you don't really have to think too hard about that for very long to realize that it's not going to get you very far, given what I've described about the things that we want to do in the WRE. So we needed a new set of tools, something that helped us deal with uncertainty in multiple sectors, and then something that gave us the ability to go and get a common understanding of the planning problem and the issues that we all face, and then bring us back to plans and strategies that we can all sign off of. And that's very much what we've been able to do with Julien, and what we hope to do over the next 18 months. I think if you're interested in an international perspective on this, I would direct you to some of the work that the US Bureau of Reclamation have done in the western states of the US. So my interest in this was really started by reading a plan for the Colorado Basin that was published in 2012. There's a big literature over there about MORDM and multi-sector planning, which again, if you're interested in this, you'll find very useful. Great, that's it from me. I think, Suraje, we're going to questions, is that right?
Yep. We're going to go into questions. So please do put those questions in the Q&A, folks. Maybe I'll kickstart with one for you, Steve. I mean, so there's been a huge development in terms of methodologies, in terms of multi-objective, robust decision making, and Julien has demonstrated this in this work. So, and it's great to see water companies engaged in this. To what extent are the regulators now starting to pick up these methods to do long-term planning under deep uncertainty?
Well, I mean, I think as a community of water resource planners, what we all recognise is the inadequacies in the old methods. So I mean, particularly in this investment planning round where Julien talked about rapid. I mean, the big idea is that there's going to be a massive investment in supply side capacity to deal with stuff like resilience. And if you go back to the old methods, single company, deterministic forecast, and all the rest of it, it is really tricky to justify large investments on that basis. And actually, the first conversations that I had with Julien followed a set of public inquiries in 2010 in the Thames Basin, where Thames Water and South East Water both proposed reservoir developments that were rejected at planning inquiry. And a lot of that was actually tied up with the difficulty of planning for that stuff using the old methods. So really the 10 years have seen these methods emerge. I think in the current planning round, they're kind of getting more mainstream. There's more acceptance of them, more willingness to commit resources to using them. And I really don't see us going backwards from this point. I think it'll just become more and more business as usual as we go into subsequent planning rounds.
Okay, thank you. I've got a question here from RO. Has existing infrastructure been considered, such as use of canal network for transfer of grey water? Julien, I think that was for you. And maybe for you. Yeah, I don't know, whoever wants to take that one.
Well, I think that's a great question, and of course we do build existing infrastructure into simulators that we build and use. I think what we'd struggle with is repurposing of existing assets to meet new needs. I think that's something that the sector finds really difficult. It is done in other places, and it leads to things like links between flood risk management and water supply and meeting environmental needs. So other people are able to do that, but it seems to be something we struggle with a little bit here. Julian, I don't know if you want to add to that.
Yeah, I can just say that because I went so quickly, I didn't give a lot of the details. But when I showed you those green lines that you saw at national scale, there was actually 3,600 of those and around. And every time that that transfer between two neighboring water resource zones could use either a river, a natural river, or an existing canal, it was assumed that it would. And so the cost of the transfer was therefore reduced. And so at that national scale, we did consider existing infrastructure, and also at the regional scale that Steve was talking about, some of the options, definitely use existing infrastructure. And the existing management and infrastructure is always present in the model, and it's just being supplemented by these new schemes. And so what the model does is that there's so many combinations. That's why we use these search or these optimization techniques. There's so many different options that you can't get your mind around it because they all interact in different ways. And so we just let the computer try, billions of options together, including the existing and the new ones. And then we let the computer kind of filter out and show us the most cost efficient and the most performance efficient ones.
Okay, there's a great question here about uncertainty that I think follows up from something Steve was talking a little bit earlier. Can you comment on how uncertainty across the decision space impacts planning? How much certainty is desirable when looking at trade-offs? Are current information products sufficient?
So uncertainty is key to all of this. I mean, the old way of dealing with uncertainty was in the balance between supply and demand, make an allowance for risk and uncertainty that typically varied over the 25-year planning period, completely inadequate for the kind of planning problems that we know we have to deal with. So the base of the MORDM process is that we are seeking robust solutions that perform well in many future different scenarios, and that's a different way of thinking about uncertainty and dealing with it. And to my mind, it ought to produce, better quality investments that are better able to deal with uncertainty and risk. Again, that's a practitioner's view. Julian might have a bit more of a sort of sophisticated answer.
Yeah, I mean, we struggle with this as well. What we're, a lot of those plots were actually multi-criteria robust optimization results. What that means is that not only were they considering several criteria, but they were also considering, like Steve said, multiple scenarios of the future. And I think the challenge for us is choosing those scenarios. So for when a water planner, do they pick 10, 100, or 1,000 scenarios that they want to be robust to? The difficulty, and this is something Suraje has worked on many years, is that when you think 20, 30, 40 years ahead, you become in the area of deep uncertainty, where it's like not only you're not sure, but you're not even sure why you're not sure, because there's going to be things that are going to happen to water supply and water demand in 30 years that we just don't have a clue about. So that's why we, some of this work attempts to move away from very classical prediction-based risk analysis and go towards more robust decision making, which is saying, all right, well, we don't really know the future. Let's identify a plausible set of scenarios, and let's try to select and invest in interventions that work acceptably across that scenario. And that perspective, that was attractive to stakeholders like Steve and Water Resource East. And generally, it's been very popular around the world. And Suraje can also talk to that because he's published a lot on those methods as well. And in fact, he introduced them to me 12 years ago. Thanks, Suraje.
No problem. Could I ask you whether you feel the regulators are now picking up these approaches, Julian? I think I asked that Steve earlier, because I guess the uncertainty is not going to go away, isn't it? I mean, we have to live with deep uncertainty. So the method needs to change. So to what extent can the regulatory planning approach cope with that deep uncertainty in your view?
Yeah, I can talk about that. I mean, Steve, do you want to say? I think you have to go, Steve. Do you want to say anything about that further? Because I don't want to make.
Yeah, briefly. Sorry, Suraje. I will just be brief. I mean, what I would say is water resource planning is one thing. Getting it paid for is something completely different. And so the kind of financial regulation of the water industry has to catch up with these methods. And at the minute, there's a bit of a lag, I think, and the economic regulator, Ofwat, I think, does struggle with the idea of robustness. I mean, it's not straightforward. As I said, this balance between paying for stuff that's needed in an uncertain future is quite a tricky problem if you have to balance that against affordability for customer bills. So, is it okay if I cut off, guys? I'm really sorry, but I'm committed to something else. Yeah.
Thanks for coming, Steve.
We'll keep going a little bit more, yeah, with Julien.
And thanks for joining, Steve. So yeah, if I can just, I mean, Suraje, that's a key question. I mean, Steve kind of touched on it in his response there. The fundamental problem is that the whole system in England and Wales is organized to regulate the supply-demand balance. And so once you had a deterministic supply-demand balance, then there was a single least cost solution that was kind of the obvious one that water companies should consider. Now, if you consider that both supply and demand are uncertain and that they could manifest in different ways, and that you consider that your investments should be able to deal with any of those futures, then you get into a completely different mindset. And very quickly, you get into one that forces you to think about adaptability and flexibility. So your question, the regulator question, is in the process of changing from what is the cheapest way that the water companies can meet future demand to what is the way that water companies should meet future demand that could adapt at reasonable cost to both supply or demand being different in the future than what we think they would be today. And so that is, now the problem with that answer is that that moves you to a field of science which we could call sort of the adaptive capacity expansion problem. In engineering is what it would be called. In development studies, it would be called it's kind of the adaptive development problem, like what human actions should be taken in order to adapt to the future, which is uncertain. And that's a much more difficult problem, not only conceptually, but also, and therefore to regulate, but also methodologically. You have to start doing multi-criteria robust adaptive optimization. And that's a frontier problem in science and engineering. So I think I think we're doing well with industry here to apply these new methods, but we are putting industry in a bit of a tight place in that, we've created demand for these adaptive and robust planning methods, but the reality is to apply those at national scale in the UK probably uses computer methods and algorithms that we don't yet possess. So, this is not a trivial and obvious, so this is a process and then not, one which has an obvious single answer. But I think the collaboration in the last 10 years has been really good, and the regulators are very open to these new methods. In fact, the Environment Agency guidelines now allows for explicitly adaptive optimization, whereas 10 years ago, no one had heard of it, and it was not found in any regulatory document, except maybe as a sort of theoretical concept. So there's been a lot of progress, and the regulators and policymakers are very open to these new methods and the benefits that they could provide.
Okay, great, thank you. If there's any other final questions, folks, put them in the Q&A. It's your last chance now. There's a good question here about the first part of the work you talked about, Julien. So how feasible are large-scale national water transfers? Because there's obvious deficits in the southeast, and so given the way current water companies are run and regulated, someone's asking about that, and maybe I'll ask what I wanted to ask in that context, which is, could you tell us a little bit about what resilience indicators you used? I noticed you had a sort of 1 in 500 event, and that sounded like it was related to a drought, perhaps. But if you could elaborate a little bit on that.
Yeah. So those are two interesting questions. I mean, the first, in the national scale work, our treatment of resilience is quite simplified in that because we're doing national scale optimization where we're looking at over nearly or around 4,000 options, both supply options and transfers. We couldn't do the traditional purely physically based simulation that we did. So that supply demand model was quite simplified. It was just looking at annual supply and demand per each of those water resource zones. So that the quantification of resilience there is very simplified, and it just limits itself to water supply schemes and how they perform in the 1 in 200 year drought or in the 1 in 500 year drought, as identified by more detailed physically based models and analyses. So, what that study was basically doing at national scale was looking at, okay, given all our hydrological models that we're using nationwide, we can identify what would be traditionally called by a water supply engineer the yield of any supply, or what in UK that we call the deployable output. And so under the 1 in 200 year drought, what are the minimum supplies that all these options could provide? And so that's what the model is trying to couple together at least cost, either for the 1 in 200 year resilience, as it's called, or the 1 in 500. Now that's a very crude way of doing it. And the only reason why we're using that is because it's at national scale and it's just such a big computer problem that we have to go through that simplification. If you look at the regional application, there we were doing it in a much more interesting way, where resilience was defined quite simply as well. Well, quite simply in that it was just the duration of failure. So, you're tracking every week what points are getting how much water and what sectors are getting what water deliveries. And then you just ask each sector, what do you consider to be a water supply failure? And they'll tell you, well, a really bad one will be we don't get any water for 2 months. A bad one will be for 2 weeks. Inconvenient one will be for 1 day. And so you create these metrics, and so the resilience is tied directly to duration of failure. Okay, so that was a bit long answer to that first question. So each scale of analysis will have a different definition of resilience. The most academically and intellectually satisfying one is, I would say, in these studies would be the regional one. For the water transfers, it's true that the water companies are organized in 20 private firms, roughly 20 private firms in England and Wales. In Wales, there's one, and it's not trivial how they're going to be institutionally motivated and incentivized to trade water. That's not a trivial question, and the regulatory regime is trying to adjust to enable and incentivize that collaboration between companies. And I would say that's only starting to be worked on, and how the regulatory regime should change to accommodate and provide appropriate incentives for water companies to both buy and sell water in a way that's in the public interest. That's still an open question. But right now, it looks like the regulators are taking a common sense approach, which is, let's look at the transfers, ignoring whether they're transferring to different companies. Look at the ones that are most in the public interest, and then those are the ones that we expect the water companies to select. So for the moment, the government and regulators are taking a pretty straightforward approach, one that is likely to be effective. So all these modeling analyses are trying to provide information to support that kind of decision making on, for example, identifying what transfers amongst the many options, which ones specifically would be the best early ones to implement.
Okay, thanks, Julien. And final question we've got here is how many water companies are you working with? And maybe I'll add to that, to what extent are water companies able to collaborate in this work, particularly maybe thinking about that context of water transfers?
Yeah, so there's all sorts of efforts going on by many universities, many consulting firms. So, these are not the main 3 ones. These are just some of the things going on. There's a national scale water resource simulator that's being done by Rapid with Oxford. We're building this national supply demand model with a lot of company representatives and with Ofwat Environment Agency. At the regional scale, each of the 6 regions of the Environment Agency has a regional project, a regional group, a little bit like the one that Steve works on. And so that what Steve was describing, that's happening for the 6 Environment Agency regions throughout England, and in Wales is doing something similar. So, you know, so that's happening. You know, so Steve's not the only one doing that. There's a lot of people doing that, and there's a very big effort, for example, in the southeast of England called Water Resources of the Southeast, and they have a website that you can read up on it. And then in the companies, you know, a lot of academics work with a lot of companies. You know, we tend to work with 1, 2, or 3 at any given time doing research, applied and peer research for them. And so, yeah, I would say most of the companies, because these methods are starting to enter into the regulatory guidelines and regulatory documents and policy documents, most of the companies are trying out these new analytical approaches that people like Suraje and I and many others academics in the UK have been talking about. And, you know, so yeah, they're being actively used, and I think it's a successful case of academic and real world collaboration.
Great, thank you very much, Julien. It's been fantastic to get this road trip across national, regional, and local scales. So thanks very much to you and Stephen for the presentation and answers and questions. I'm going to just share my screen one last time to just mention the next webinars that we've got planned. So, oops, let's see if I can just, okay. Can you see the slide, Julien? Yeah.
Yes, we can.
Okay. The next webinar we've got is by Dr. Liz Sharp from the University of Sheffield. So she'll be talking to us about the feasibility of domestic rain tanks contributing to urban flood resilience. And then afterwards, we continue the flood themes. We've got Paul Sayers from Sayers and Partners to come and talk to us about an event-based assessment of the impact of climate change on future flood risks. So do go to our website where you can register for these webinars. So as I mentioned earlier, the webinar was recorded, so we'll put this up on the website as soon as we can, along with the slides. Yeah, thank you for watching, and we'll be back in a couple of weeks' time. So until then, thank you. Goodbye.